Greetings and welcome back. Today we're going to be looking at an introduction to ketones and aldehydes. So remember that both of these are your kind of generic carbonyls. The ketones involve an R group on both sides, and aldehydes have an R group on one side and a hydrogen on the other side. Also, a molecule that has a hydrogen on both sides, which is formaldehyde, is also considered to be an aldehyde as well. Despite the fact that this lecture is entitled Introduction and Nomenclature, we're going to start with nomenclature first and then get into a little bit of the kind of reactions and the general information about what ketones and aldehydes can do. So let's start with naming. When we name a ketone, naming ketones, we'll start with ketones first. What you want to do is drop that last E at the end of the name, and you replace it with -one. So an alkane becomes an alkanone. So for example, here's a 5-carbon ketone, and instead of being pentane, we would drop the E at the end, and it would become pentaneone. So notice we didn't turn the ane into an one, we just dropped the E, so it remains pentaneone. We have to say specifically where that is, so we would number it using the same rules of numbering that we've always done. And this would become 2-pentanone. Or, of course, you could also say pentane-2-one. All right, in order to name aldehydes, what we do is we drop that E at the end, and we replace it with al for aldehyde. So for example, here is a, how big is that? That's a 7-carbon chain. And instead of being heptane, we would drop the E at the end, and this would become heptaneal, or heptanal. In this case, we don't have to number it, because an aldehyde is always going to be at the end, so it's always going to be at carbon number 1. Therefore, there's no reason to put that in there, because we know that it's always at carbon number 1. Everything else must be relative to that. In terms of priority, remember we've talked about the priority of functional groups, and this applies to both the who gets to be the part of the main chain and who has to be a substituent, as well as where you number from. Our number 1 is going to be our aldehydes, and then we're going to have our ketones, and then we go into alcohols, and then etc., etc., etc. After alcohols would come alkenes, alkynes, etc. So as of now, aldehydes are the highest priority functional group, and ketones are the second highest priority functional group, and then alcohols would come below that, etc., etc. To name these guys as substituents, in both cases, we would call them oxo groups. If you want to name something as a substituent, basically what you're saying is that it's not the highest priority thing. I'll give you an example of that in a second, but if, for instance, we had a ketone and an aldehyde, the aldehyde would become the name, so it would be an alkanal, and the ketone would have to be called an oxo at whatever position. And you put it in the front just like you would a methyl or a chloro or whatever. So let's try this one. I will ask you to pause this and see if you can name this molecule. And then we will go through it together as an example. All right, welcome back. let's number this guy. We would number from the aldehyde, which is on the far right, carbon 1, 2, 3, 4, 4, 5, 6. So therefore this would be a 6-carbon chain, which is a hexane. It's an aldehyde, is our highest priority functional group, so it would be a substituted hexanal. Again, we don't need the number on that because the main chain is the aldehyde, which is always at carbon number 1. So this alcohol would be a substituent, and this ketone would be a substituent. The ketone as a substituent is an oxo group, that's at position 2, so that's a 2-oxo. And the alcohol as at carbon number 5, and that's called a hydroxy. Therefore, we would alphabetize these things, and the name of the molecule would be 5-hydroxy 2-oxo hexanal. And that would all be one word. If you have a ring with a ketone, it doesn't really matter very much. So remember, if we've had our highest priority functional group on a ketone, or on a ring, excuse me, then we don't have to number it again. You just start at number 1. So see if you can name that one, and then we'll come back together and do it. So in this case, the main chain, of course, would be the cyclohexane, but it would be a cyclohexanone because it has a ketone as your highest priority functional group. You don't have to number it because the ketone comes at carbon number 1. It's the highest priority thing. So in this case, we would actually have also this alkene at carbon number 2. So we would replace the ane with an ene, and this would become 2-cyclohexenone, or you could say cyclohex 2-ene own. And in neither case do you have to worry about putting the 1 with the ketone, because the 1 is generically going to be the definition of our highest priority functional group's location. All right, what if you have a ring with an aldehyde coming off of it? Well, this gets a little bit weird because that aldehyde is not actually part of the ring. The aldehyde is kind of a 1-carbon thing off to the side, and then the ring would basically be a substituent. If you have this very particular example, where you have something with an aldehyde coming off of this type of ring or a benzene ring or something like that, it is the highest priority functional group, so it would get the name. But what we do is we name the other part of the ring, so this would just be a cyclohexane. And then you would put on the word carbaldehyde. And that means essentially you have a 1-carbon aldehyde, and you're just naming the rest of the molecule kind of as its own sub-main chain. So this would become a cyclohexane, and you would name it as the carbaldehyde in terms of where that thing is located. This would be manifest in something like, move that guy up here. Here's a little bit of a trickier example. What if I had something like this guy? See if you can name that one. In this case, we have to number it 1, 2, 3, 4. We would want to start at number 1 because that would be our carbaldehyde. So right off the bat, we know that we're going to have a 1-carbaldehyde at the end of our name. And we would have a cyclohexane here, which has a 4-iodo and a 3-isopropyl. So the 4-iodo would come first because iodo comes before iso. 3-isopropyl. I might not be able to fit this. Oh, it won't let me move them separately. Sorry, I'll have to interject in the middle here. Cyclohexane. So it would be a 4-iodo, 3-isopropyl cyclohexane, carb 1-carbaldehyde, because the carbaldehyde is coming off of position number 1. So it's a little bit of a mouthful, but notice that we don't want to name everything as a substituent on a methanal. So instead we use the term carbaldehyde. So basically you take the rest of the molecule, what I circled in green there for the name, what I'm circling in green here for the molecule, and we say, yeah, we know we have this carbaldehyde at the end. But instead of naming all of that as substituent on substituent on substituent, we basically make this part that I've circled in green as as kind of a pseudo main chain. We just name this guy as your main chain, and then you just stick carbaldehyde at the end, because carbaldehyde is the highest priority functional group. I don't want to spend a lot of time on these, but let's look at some common names. The common way of naming ketones is to consider, it's kind of like ethers, where you just name the two things on either side of the ether. So what we do here with common names, remember this is not IUPAC, and sometimes they're not used very commonly, they're just called common names, is that we have a ketone, and there's a methyl group over here, and an ethyl group over there. So the common name of this would be methyl, ethyl, ketone. Generally, we use this for very simple molecules. It's not used very often. But here are some common names that you do need to know. These get used in IUPAC as well. This one with 2 acetyl groups, this is acetone. Acetone is something that we've used quite a few times in lab. It's a very, very common solvent. The acetyl group attached to a phenyl ring is called acetophenone. And that's a name that you need to know. And then we also have some common names of some aldehydes that you need to worry about. We mentioned this one at the very beginning. This one is formaldehyde. Formaldehyde is obviously a very common molecule. Less common, but still important to know, is acetaldehyde. So you'll notice that acetone comes from the acetyl group, which is a C double bond O CH3. Acetophenone has the acetyl group as well, C double bond O CH3. In acetaldehyde, again, you have the acetyl group, the C double bond O CH3. So that's where that guy keeps coming up again, the acetone, acetophenone, and acetaldehyde. There are names for all of these aldehydes as well. There's common names, but I'm not going to ask you to know the other ones because you'll probably be able to recognize them. So for example, this guy is called butyraldehyde. But you probably noticed that the butyl, that's 4-carbon chain. So butyraldehyde, that's actually where we got butyl from. Butyraldehyde is something that had been used very commonly, and therefore the 4-carbon chain in IUPAC just became butyl. So this is a way that actually we got an IUPAC name or prefix from a kind of an old-timey name that had been used a lot for something extracted from butter specifically. In the common names, the substituents are usually not used, they don't usually use numbers, so they use the letters, Greek letters, indicating how far away things are from the carbonyl. So alpha, beta, gamma. If you had something on that gamma position, it might be gamma amino butyraldehyde or something like that. So if you ever see the Greek letters, usually what they indicate is how far away you are from that carbonyl. Those are only used in common names, and you see them a lot of times in biochemical names. All right, so that's it for common names. The only ones that you really need to worry about are not this one, but the ones above it: acetaldehyde, formaldehyde, acetophenone, and acetone. You're not even going to need to worry about the methyl ethyl ketone and things like that. But hopefully it makes sense. It's not too challenging, but it's of limited usefulness to very big molecules. And that's why, once again, we use IUPAC almost exclusively instead of these common names. Lastly, I'd like to give you a very brief introduction to how these guys act or react. The main driving force for the reactivity of carbonyls is, of course, that we have a very polar bond going from the carbon to the oxygen itself. So if this is formaldehyde and this is acetone, you can see that acetone is much more stable because you've got carbons donating electrons towards that electron-deprived carbon, whereas in formaldehyde you don't have anything like that going on. So the reactivity is that you have very strong electrophiles specifically located at that carbonyl carbon. So right there, that guy's an electrophile, and right there, that guy's an electrophile. They're pretty similar because it's a C double bond O, but because of the fact that in a ketone you've got electrons kind of filling that void a little bit, aldehydes are much more reactive or stronger electrophiles because they don't have those carbon next doors or carbons next door, kind of allowing that carbon to have part of its electron void filled. And relative to aldehydes, ketones are weaker electrophiles. One thing we see with all carbonyls, and this is happening all the time whenever you have anything in water, is what's called hydration. So let's look at acetone. And what can happen when you put this guy into water, it would go back and forth, is you would add a water on. So you'll see hopefully how this can happen. Water can act like a nucleophile and attack that guy. If you just did it that way, and that's not ever the way that the mechanism works, you would get an O- and an OH2+. Of course, that would not be very stable, so instead what happens is that you get an OH on both sides. And this guy is called a hydrate. So all of these, all ketones, all aldehydes, with some water in their solution, are going to go back and forth. This equilibrium exists between the carbonyl and the hydrate. And this will happen to both ketones and aldehydes. In this case, of course, it is a ketone. Because ketones are less reactive or weaker electrophiles, and aldehydes are stronger electrophiles, in aldehydes they tend to favor forming the hydrate, and in ketones they tend to favor leaving it as a ketone or an aldehyde. So a lot of times formaldehyde, a bottle of formaldehyde, is not really formaldehyde by itself. Formaldehyde with water tends to form almost exclusively its hydrate because that electrophile is so strong. With ketones, they tend to stay like this, although they can turn back and forth into their hydrates. So if you ever see something, it kind of works the other way around, if you ever see something that's a geminal diol, that is to say right here you've got two alcohols coming off of the same position, this isn't used very much as a functional group because it doesn't really exist like that for very long. Those geminal diols are really just ketone or aldehyde hydrates, and they tend to go back and forth to their ketone or their aldehydes. So with an aldehyde, you tend to favor more the hydrate, and with a ketone, you tend to favor more the starting material, the ketone or the aldehyde proper. All right, next we'll move into how to synthesize these molecules and then also reactions of them. So have a great day.